to class. Okay, so we talked about gravity. Now let's talk about, everything else. Now, pretty much in this class, everything else is electromagnetic in nature, basically electrical in nature. If I push on an object, why is this object moving? It's like the electrons in my fingers are interacting with the electrons in the eraser. They're repelling each other. That's why this thing is moving. So, but we don't, we have an actual force for like charged particles interacting with each other. And in theory, we could analyze it that way. Like just say, look at the electrons, in your fingers and the object you're pushing and how they're interacting. That would be like hopelessly complicated. But in general, we can just say like a force is a push or a pull without getting into these microscopic details of what's going on. And so basically what we do is we kind of give names to forces. So let's go back to this book on the table. So we know there's gravity acting on it. So let's actually get a book. So gravity is pulling down. The surface here is pushing up. And earlier I said that's the force that the table's exerting on the book. However, we give this a name, and we call this the normal force. Now, what the normal force is, now I'm writing out the names. Pretty much down the road, here's how we would do this. For the normal force, I'm just going to write Fn. And for gravity, we could write Fg. Or gravity, I usually just write mg because that's how we would calculate gravity. But we call it a normal force, and that name means something in math and science. I'm not quite sure why, but normal means perpendicular. So this is like a contact force. There's a, like the bottom of the book and the top of the table are interacting with each other, and they're the normal force, pretty much by definition, is perpendicular to the surface of the object. So like here, the normal force points upwards. If we have, say the book was on an inclined plane. So in this case, we have gravity, which is straight down, and then we have a normal force. And again, normal force is always perpendicular to the surface. And again, that is just by definition. Now, let's say we have this book on an inclined plane, and it remains at rest. So, like, if this was, like, say this was like a metal ramp, and you place a block of ice on it, is the ice just going to sit there? No, of course not. It's going to slide down. And, but if we have like a rough surface and we place an object on it, maybe it's going to just remain sitting there. And that's because there's another force, like gravity is trying to pull this down, but because of this, it's on an inclined plane, we can break gravity up into components. So we have a component that's, parallel to the normal force and one perpendicular to it. And the normal force is going to kind of cancel out this component of gravity, but there's going to be a component of gravity down the incline that's going to cause it to accelerate downwards. But there's also another contact force between like the book and the surface here, and that's called friction. We use a lowercase f to describe friction. And so really, the force between this surface, like between the book and the surface that it's resting on, it's really the normal force and friction combined. So you can just say there's a force between the inclined plane and this book that's, in some direction like this. There's going to be a contact force here. But we never really do that. What we do is, let's say we can always break forces into components. So let's break it into one component in this direction and one component in this direction. And we're just going to call this the normal force because it's perpendicular to our surface. So the actual force might not be perpendicular, but just think of this. This is a component that is perpendicular. So normal forces are always perpendicular. And again, we're just giving it that name, normal force. Oh yeah, something else I have to talk about. I wish I didn't have to talk about this. Let's go back to the force of gravity. That has another name, which is called weight. And it's one of those terms, we could just delete that from our memory and we'd be fine in a physics class. We never need this term weight. Just think weight is the force of gravity. Okay, so normal force, that's just a name we give to any force that's perpendicular to a surface. And that's important for the next force we're going to talk about, which is friction. So again, like say I'm exerting a force on this marker, and you can see if I apply a steady force, this marker just moves at a, if I push it at a constant speed, it's just going to go at a constant speed. So let's say I'm exerting a constant force on it. Normally, if nothing else was going on, if you exert a force on an object, you're going to cause an acceleration. So if I exert a constant force here, it's not accelerating. It's just going at a constant speed. And so what I'm doing is I'm sliding this marker across, or this eraser across the surface. And so this is like one object moving across another. And the force is called friction, which is an opposing force. So again, let's say we have an object that's moving, say, to the right. There's going to be a force called friction opposing that. So let's say I get this thing moving. This isn't going to happen for long, but yeah, you can see it when I wasn't touching it. It moves for a ways and then stops. That's the frictional force. So like it's moving to the right, but friction is causing it to accelerate to the left, which will make it slow down. Now we can write the frictional force in a very simple way. I'm going to kind of condense what we had earlier. Okay, so everything I erased is back, but just with a little more room here. And so we can say the frictional force is proportional to the normal force. So if you double the normal force, you double the frictional force. That's what that direct proportion is. But in order to turn it into an equation, these two forces are not numerically equal to each other. It's just a proportional thing. So your force is proportional to the normal force. And in order to turn that into an equation, we need a constant, which we call mu. That's a Greek letter. Now notice that mu is a force divided by another force. Like if we solve it, that'd be the frictional force divided by the normal force. And so this is just a number. It doesn't have any units. It's newtons over newtons. It is just a number. Now, what is that number? It depends. Mainly it depends on what the two surfaces are. So I've got a table in the book where we have like a coefficient of, it's called the coefficient of friction. And I've got some values like glass on glass. So say you have like a glass object moving on another glass object. Or not even necessarily moving, but the force of friction can exist either way. So glass on glass, 0.94. Ice on ice, is 0.1, much smaller value. And you know, ice, like say you have like ice outside, like an ice rink for skating. If you take an ice cube and just slide it, it's going to go a long ways. There's not that much friction between them. Or if you have a glass surface and you place some glass on it and push it, it's not going to go very far because there's a lot of friction there. Another important one is rubber on dry concrete. Rubber on dry concrete is 1.0. And then we can also look at rubber on wet concrete, 0.7. So why this one's important, think driving on concrete, your tires are made out of rubber, so there's a lot of friction between the tires and the ground. But if it's wet, if you're driving on a wet road, the frictional force decreases significantly, and that's not good when you're driving. You want friction when you're driving. Helps you control the car and change your speed, speed up, slow down. That, especially the slowing down part, can be important. Okay, so this is just some values. And again, whenever you look up data, just look up data in a table like this, you always have to read the fine print because these are taken under certain conditions. Like one in particular, rubber on dry concrete, it says 1.0. Again, there's different types of rubber. And if you ever watch car races, like on TV or something, like before the race starts, when these race cars are all just at the gate waiting, notice they're spinning their tires a lot. They're doing that for a reason. They're trying to heat up the tires because you actually get more friction that way. So like these values can depend on other factors like temperature. And again, like different types of rubber, some will be better than others. But, if you're an engineer, you want to worry about those details. For us, we don't really worry too much about it. So like right now, it looks like this friction force is a very simple thing. F equals mu Fn. And you just look up mu in a table and you're done. But we have to be a little bit careful because it's not quite as simple as it seems. For one thing, there's more to this table than I've shown you. But let's, I guess I'll leave this table for now. And again, there's more examples in the table. But this is, for now, I'm just going to call that mu. Okay, but let's look at a simple example. Let's say we have a 10 kilogram mass. And let's say I push on it with a force of 20 newtons. And let's say the coefficient of friction between these two surfaces is 0.7. Okay, now this 20 Newton force, that's just a pushing force. We often call that just an applied force. That's just a general term for some force that we're applying if we don't have any other name for it. So an applied force of 20 newtons. And so I apply a 20 Newton force. Now friction, we're going to try and cause this object to move to the right. So if we're trying to push an object to the right, then the frictional force is going to be frictional force always opposes what you're trying to do. So like you push it in one direction, friction force is in the opposite direction. So we push it to the right, friction is to the left. Also here we have gravity and a normal force. And let's try to analyze this using Newton's laws, which, put it up here. Now again, we're going to go into a lot of detail on Newton's laws, but remember it's vectors, so we look at the x direction and y direction separately. Now the force of gravity is mg, that's going to be 98 newtons. And the normal force has to be 98 newtons as well. Just because, nothing's going on vertically. We're applying a horizontal force, it's not moving up or down. So these two forces have to balance each other. So 98 up, 98 down. But now that we know the normal force, let's calculate the frictional force. So we'd have 0.7 times 98 newtons. So let's do that. 98 times 7. 0.7. So I'm getting around 69 newtons for friction. So what this is telling us, let's call this the x direction. What this equation is telling us, if we just kind of blindly follow it, let's say we have an object here. Let's imagine that this eraser is 10 kilograms, which would be kind of ridiculous. I think that's like 22 pounds or something. But let's say I apply a force. I push it to the right. Now, if we look at this picture, it looks like the net force is going to be 49 newtons to the left. So if I push this, I should expect it to accelerate to the left. It's not doing that. And of course, we wouldn't expect that in reality. So this frictional force, it's not actually 69 newtons according to this equation. What is it? Let's say this is our 10 kilogram mass, and I push with 20 newtons. What's going to happen is nothing. It's not going to move. Friction is holding it in place. And that's what this 69 newtons represents. Or in general, this mu Fn, that is the maximum friction force. So in this case, if I apply 20 newtons, friction is going to reply with 20 newtons in the opposite direction. If I push harder and increase this to 30 newtons, friction is going to reply with 30 newtons of force. It's just going to match whatever you push on it with until you get to 69 newtons. So let's say we go to 70 newtons. Well, now friction topped out at 69 newtons. Sorry. And so now there's a net force of 1 newton in the direction that you're pushing it. And now it's going to kind of break free and start moving. So this, really what we should write this as is frictional force is less than or equal to the normal force, mu times the normal force. But I didn't bother doing that, I just wrote this. But we're actually not done talking about friction yet. Very important to understand that though, that this number you get by calculating UFN, that's just a maximum force that friction can provide, not necessarily what it will. But let's go back to this example. I kept increasing the force, and then I got to like 70 newtons. That was enough to overcome friction, and so this thing is going to start moving. And now what we're going to find, though, is this force is going to decrease. The frictional force is now going to decrease. And the reason why is initially this object, like what is frictional force fundamentally? And what it is it's an interaction between the electrons in the objects and the two objects. And again, this looks like a pretty smooth surface. Table looks pretty smooth. But if you were to zoom in with a microscope, they'd be much more jagged. And yeah, you can have regions like this, where you've got one surface looks like this, and the other surface looks like this. And in areas where they come very close to each other, the pressure there can be so great that it actually kind of welds these molecules together. So like the molecules in the eraser are melding with the molecules in the table. And if you want to get this thing moving, you have to break those bonds. And once you get something moving initially, again, it's going to be, these bonds are going to be constantly forming and breaking as it's moving, but it's much easier to keep something moving than to get it moving in the first place. So like first you have to break the bonds, and then they'll be reforming and breaking much more rapidly. But yes, we have to distinguish between two kinds of friction, which we call static and kinetic. And so like right now I'm pushing on this and it's not moving. This is static friction. Now we're dealing with kinetic friction. Kinetic friction, it's probably better to think, instead of like moving friction, think sliding friction. The table's not moving, but the marker is. And so like the eraser is sliding over the table. So that would be an example of kinetic friction. And it's the same formula, but we just have a different mu value. So these values I gave you before, these were for static friction, but for kinetic friction, I'll write down those numbers as well. For glass on glass, we can see there's an enormous difference. We go from 0.94 to 0.4. So that's a huge difference. Ice on ice, that's also a very significant difference. From 1 to 0.2, that's a factor of 5. Rubber on dry concrete, not that big of a deal, from 1 to 0.8. And kind of similarly here. So again, this distinction between static and kinetic friction. Static is when it's not sliding. And kinetic is when they're sliding past each other. And it's important to, I stated it in a particular way. I said static is when it's not sliding. I didn't say when it's not moving, because there's a very important example. Let's look at this marker. Is this an example of static or kinetic friction? And actually, this is static friction. It might not look like it because the marker is moving. Isn't that what kinetic friction is? However, it's doing something we call rolling without slipping, which is something we're going to talk about quite a bit later on. And if you look at, it's obviously moving to the right, but, if you look at it rolling, if you look at the bottom where it's in contact, if I'm spinning this, it's like this point, if you just trace it, it's moving to the left as it's spinning. Like the point that's on the bottom, the way I'm spinning it, it's always moving to the left. And so if the marker's moving to the right, if you just look at that point of contact, the marker's moving to the right, but the point itself is moving to the left. And when they're rolling without slipping, they're doing it in a way that those cancel out. So there's no relative motion between the point of contact and the surface itself. And that's usually what rolling objects do. Now, that's not always the case. You can imagine, say you're driving and you slam on the brakes and your tires lock up and just slide across the pavement. That would be kinetic friction. But your brake system is actually designed to prevent that from happening. There used to be a term called anti-lock brakes. I don't think they even call it that anymore because it's just the standard. But I remember they were like a new thing. Like in old cars, you hit the brakes, and if you hit too hard, they'll just lock up. And nowadays, brakes are designed so that it's much harder to cause them to lock up, because that would switch from this rolling friction to where if the tires lock up and they're sliding, you lose friction due to that sliding. And so, so it's possible that you can have like a spinning wheel that would be an example of kinetic friction. But usually, if you're just like driving, that's an example of static friction. Because the combined rotation and just linear motion work just right to keep any relative motion between the point of contact and the ground. So friction is actually a fairly complicated thing because there's two types, and we have to remember in the static case, that would be mu Fn. Where we could write the kinetic case with an equal sign. And just one more thing I'm going to say about friction right now is you have to be a little careful with the normal force. Because a very common thing to do is just say, like, let's say we look at this example where we have a mass, gravity is mg, normal force is upwards, and so we can see that the normal force is equal to mg. And that applies in this case But if you place a mass on an inclined plane, that's a different story. So like here, the normal force is in this direction, and gravity is straight down. In this case, the normal force is not equal to mg. And I'll make sure to do an example of this, in class during our review. But it's just a common mistake I see to always associate the normal force with mg, when that is not always the case. In general, that's only the case when you have a situation like this. So just don't assume that the normal force is equal to the weight, or the force of gravity. All right, so we talked about, let's make a list. We have gravity, normal force, friction, which comes in two types, static and kinetic. I want to talk about another one that's important called tension. So let's say we have an object, and I attach a string to it. And let's say I exert a force of 10 newtons on the string. Now I want to know what's going to happen to this object itself. Let's say this has a mass m. So if nothing else is going on, let's say this is on wheels. So say friction isn't a really big deal here. So we pull on it, we'd expect this cart to move, especially if we ignore friction. But my question is, what is the force on this object? Now you'd intuitively say, well, 10 newtons. But 10 newtons is the force acting on the string, but what is the force acting on the object itself? And that's a little more complicated. I'll give you a little spoiler alert here. It's going to turn out to be 10 newtons, but it's not always going to be the same. It doesn't have to be the same. But for the problems we're going to be doing here, it's always going to work out that way. But let's look at it in a little bit more detail. Actually, let's call this M1. And let's call this string M2. And so what we're doing is we have two objects here. We're exerting a force on mass 2, and it's the string that's exerting a force on mass 1, which is this cart. So let's draw these as two separate objects. We have M1 here, and our string over here. And so again, applied force. That's just a general term. So we exert a 10 Newton force on the string. And the string is going to exert a force on this mass. But we don't know right now what that is. So let's call this F12. So like the force on mass 1 due to mass 2. Okay. Now, by Newton's third law, if the string is exerting a force on mass 1 is exerting a force on the string. We call that F21. And these two forces, these are an example of Newton's third law, so they're equal in magnitude and opposite in direction. And so if we look at the string, let's say this is our x direction, the net force on this object is 10 newtons minus F21, and that would be the mass of the string times the acceleration of the string. Okay. Now, let's consider case 1. Let's just say the acceleration is 0. Again, say this is a sled and you're pulling on it with a rope. There's no acceleration. You're just walking at a constant speed. If the acceleration is 0, then the right side is 0, and we'll see that this force is equal to 10 newtons. But what if you're accelerating? Is that still going to be the case? Not really. If we solve for F21, we get 10 newtons minus the mass of the string times the acceleration of the string. And here, yeah, so this force will be a little less than 10 newtons. How much less? Basically 0. Because a string, string is actually a very, very strong thing. You can support a very large mass with just like a thin string. And so typically the mass of the string is so small, we don't care about it. So even if there is an acceleration, let's just ignore that. And so typically we just say that F21 is 10 newtons, which means that F12 is also 10 newtons. So for this class, we're always going to assume that our string is so insignificant in mass that they just perfectly transmit forces. So if you exert a force of 10 newtons on this end of the string, that's going to exert a force of 10 newtons on like the other end that's pulling on this object. So we're going to consider strings as just perfectly transmitting forces, which is not always the case. But to a very good approximation, it will be. All right, just going to make sure I'm not ignoring anything important. Yeah, I think we covered all the forces that we needed to. And again, we'll do some examples in class. So I think this has gone on long enough. I don't want to give you too much, take too much of your time. So I think we'll stop this here and then just review this during class. So that'll be all for now.